Hello everyone. Let me begin today's session with a question. Can you imagine a world without sanitizers, perfumes, fuel additives, or even soft cosmetics like creams? All of these depend on one class of compounds, alcohols. Alcohols are not just laboratory chemicals, they're present in medicines, fuels, antifreezes, and even in the beverages we consume. Among them, four stand out as the most commercially significant: ethanol, methanol, ethylene glycol, and glycerol. Their wide applications are rooted in their chemistry, particularly hydrogen bonding, polarity, and the versatile hydroxyl group. So as we go ahead, keep in mind, understanding alcohols isn't just about memorizing structures, it's about seeing how deeply they shape both our industries and our daily lives. Now let's begin with ethanol, the most familiar alcohol. Many of you already know ethanol as a drinking alcohol, but its story starts with fermentation. Glucose, with the formula C6H12O6, breaks down anaerobically with the help of enzymes to give 2 molecules of ethanol and 2 molecules of carbon dioxide. So the equation goes C6H12O6 gives to C2H5O plus 2 CO2. That's the principle of brewing and winemaking. Industrially, ethanol can also be made synthetically by adding water across the double bond of ethene, using concentrated sulfuric acid as a catalyst. Ethanol's uses go far beyond beverages. It serves as a solvent in medicines and perfumes, as an antiseptic in hospitals, and when blended with petrol forms gasohol, an eco-friendly renewable fuel. To obtain pure, absolute ethanol of 99.9%, chemists use azeotropic distillation. Remember though, ethanol, while relatively safe, can still be harmful when consumed in excess. Next comes methanol, often called wood spirit. Historically, it was produced by destructive distillation of wood, but modern industry relies on catalytic hydrogenation of carbon monoxide. The reaction is carbon monoxide plus 2 hydrogen gas molecules gives methanol, CH3O. This is carried out over a copper zinc oxide catalyst. Methanol is an excellent solvent and a useful fuel, and it's also a starting material for formaldehyde, which in turn is used in plastics and resins. But here's the danger: methanol is highly toxic. In the body, liver enzymes oxidize methanol first to formaldehyde, then further to formic acid. These products damage the optic nerve, leading to blindness, and ingestion of even 30 milliliters can be fatal. That's why industrial methanol must never be confused with ethanol. Now let's turn to a dihydric alcohol, ethylene glycol, also known as ethane 1,2-diol. Its structure is HCH2CH2O with 2 hydroxyl groups. It is prepared by adding water to ethylene oxide. Ethylene glycol is a colorless, viscous, sweet-tasting liquid. Its most famous application is as an antifreeze in automobile radiators because it lowers the freezing point of water. It is also an important building block in the production of synthetic fibers like terylene and Dacron. But, just like methanol, the sweetness of ethylene glycol makes it deceptively dangerous. Accidental ingestion can be deadly. So while it saves engines from freezing in cold climates, it must be handled with care. Let's move now to glycerol, a trihydric alcohol with the structure CH2O, CHO, CH2O, that is propane 1,2,3-triol. It is produced as a byproduct in soap manufacture through the saponification of fats and oils. Unlike methanol and ethylene glycol, glycerol is non-toxic. It is colorless, viscous, and forms strong hydrogen bonds, making it highly hygroscopic, which means it attracts and retains moisture. Because of this, glycerol finds applications in cosmetics, food industries, and pharmaceuticals. Interestingly, it also plays a role in explosives when nitrated with nitric acid, Glycerol forms nitroglycerin, an extremely powerful explosive. So one molecule, depending on context, can moisturize skin or power dynamite, an excellent example of chemistry's dual face. Now here's a very exam-relevant comparison. Why is methanol toxic while ethanol is relatively safe? The answer lies in how they are metabolized in the liver. Methanol is oxidized first to formaldehyde, then to formic acid, and this accumulation of formic acid causes metabolic acidosis and damages the optic nerve. Ethanol, on the other hand, is oxidized to acetaldehyde and then to acetic acid, which can be metabolized safely by the body. That's why methanol poisoning is treated with ethanol, because ethanol competes for the same enzyme, alcohol dehydrogenase, and prevents methanol from being converted into toxic products. So the equations go like this: CH3O oxidized to HCHO, then to Cu. Whereas C2H5O oxidized to CH3CHO, then to CH3Cu. This is a powerful example of how two seemingly similar molecules behave so differently in biology. So let's wrap up by revisiting the highlights. Ethanol is our everyday alcohol, used in fuels, medicines, and beverages. Methanol is valuable industrially but extremely toxic if ingested. Ethylene glycol is the antifreeze that protects car engines in winter and a precursor for polymers, though dangerous when consumed. Glycerol is safe and widely used in cosmetics, food, and medicine, but its derivative nitroglycerin is an explosive. The key insight here is that alcohols combine immense utility with potential hazards. Their applications must always be balanced with safety. So to sum up, alcohols are not just organic compounds, they are the backbone of industries, energy, medicine, and even explosives. I hope this session helped you see how chemistry connects directly with real life, sometimes in comforting ways, sometimes in dangerous ways. Catch you in the next class with more fascinating reactions and connections that make chemistry the invisible power in our daily lives.